Okay, so we have a differential equation to solve here, and the first thing you want to think about when you solve a differential equation is classifying it, because all of the different strategies that you use have to do with what type of differential equation it is. So we can see here we have a first order ordinary differential equation, because we just have a first derivative here, and it's an ordinary derivative. And then we've really learned at this point two methods for solving first order differential equations. We've learned to solve linear differential equations and separable differential equations. So in order to be a separable differential equation, I would have to be able to write the differential equation in the form dy dx equals some function of x times some function of y. And then I could manipulate the variables to separate the variables and solve it that way. So you can kind of just think through the algebra here. That's not going to work for this one. For a linear differential equation in standard form, we would want to write that in the form like this. And so you could notice right here that with the y squared and the y times dy dx that this differential equation is not linear either. So at this point you might say, well, then those are the only two things we've learned. So this is a little bit of a tricky one, sort of not the first example you would want to start with this. But this one actually is not separable and not linear in y. But this is treating y as the dependent variable and x as the independent variable. If I treat x as the dependent variable and y as the independent variable, then you can sort of rewrite this so that you have a differential equation of that same form, but switching the role of the two variables. And this differential equation actually can be rewritten in that form. So this differential equation is not the typical linear differential equation, but it is of this form, and we would say that that one is linear in x. Most of the ones that we've worked with have been linear in y. So this is a much more difficult problem, and probably not something I would expect you to recognize, that this is linear in x rather than linear in y, especially on an exam or something time limited like that, without a hint to think about this as being linear in x. But once I tell you that it is, then you can treat it as linear in terms of x and instead of in terms of y, and solve it using the same strategies we did for the ones that were linear in terms of y. All right, so I need to do a little bit of manipulation here. The first thing I'm going to do is multiply through by dx over dy. So you have a theorem from Calc 1 that a lot of times students don't remember that says that 1 over dy dx is equal to dx dy, as long as your function is differentiable. So I'm going to multiply through by dx over dy. Looks like these should cancel as a fraction. They don't exactly cancel that way, but they do cancel via that theorem. So I've now got my differential equation in terms of dx over dy instead of dy over dx. And then I need to do a little bit of rearranging so that I can get it in this form. I'm going to move all the terms to one side of the equation here. So not all the terms to one side. All the terms involving x to one side. I'm going to leave the constant term 1 on the other side of the equation. And then I want to get it in this form, just like we did with the standard linear one, so that we can find that integrating factor, multiply through, use our product rule, and integrate both sides. So I need to divide through by 1 plus y squared. You'll notice on this term, I was kind of careful in how I arranged that so that I got my function of y times x, so that we're in this form here. This is the standard form you want it in. And then you can find your integrating factor. So our book likes to use rho for that. E to the integral of this p of y function in this case. Okay, so there's a little u substitution that happens there. U equals 1 plus y squared. Your du is 2y dy, so you've got this extra negative sign. So you'll end up integrating e to the integral of 1 over u du with a minus sign out front. So you end up with negative ln of the absolute value, although you can neglect that because your u is 1 plus y squared. So simplifying that, remember that you can use that property of logarithms to write this as e to the ln of 1 plus y squared to the negative 1, and then your exponential function and logarithm function undo each other. So there's your row. That's what you want to multiply through your differential equation by. I'm going to write this as 1 over 1 plus y squared, since that's what I already have here. Here, I already have a 2y over 1 plus y squared. So when I multiply that by 1 over 1 plus y squared, I'll have 1 plus y squared squared on the denominator. And here also. All right, so then I want to go ahead and integrate this. So I want to notice here that on the left side, what I've really got here is product rule. So I want to rewrite this in terms of product rule. Notice that this is a differentiation with respect to y. So this is d dy of the product of 1 over 1 plus y squared. You can check that the derivative of that is what we have here, times x equals 1 over 1 plus y squared squared. All right, and then we want to integrate both sides with respect to y. And so over here, our differentiation and our integration undo each other. And over here, we need to go ahead and do this integration. So you do that integration. There's some algebra that or some trig substitution that you're going to need to do there to do that. So you're going to do a trig substitution. Y equals tangent theta. Dy is secant squared theta, d theta, and make your substitution. So I have secant squared theta. My 1 plus tangent squared theta is secant squared theta, and the quantity squared. So I'll have one of those to cancel. I'll be left with 1 over secant squared theta. So that's the same thing as cosine squared theta. And I need to go ahead and do that integration. I'm out of space here, so I'll go ahead and just write down the answer over here for the integration for that. You then need to back substitute for your theta. So do your back substitution for that. And then you've got a complicated solution that is implicit because it's not solved for y, but a solution to the differential equation. Here I'm going to need a right triangle for my trig substitution. Tangent theta is opposite over adjacent, and so the hypotenuse here would be square root of y squared plus 1. Here I'll need to use a trig identity. Sine 2 theta is 2 sine theta cosine theta. My 2's cancel. My sine theta and cosine theta I'm going to get from my right triangle. Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So I'll have y over the square root of y squared plus 1 times 1 over the square root of y squared plus 1. I can simplify that, plus c. All right, so there we have a big old messy solution, but a solution nonetheless to this differential equation. So there's one of these in your homework, so just try that. I think it does have a hint that the differential equation is linear in x rather than linear in y. And so the really difficult thing here was actually the integration. Generally, it might be a little bit easier. I think the one on your homework is a little bit easier to finish, so try that one.